It's great to be here with Rocío and Matías talking about the synthetic controls and the regression discontinuity design. And yes, and the first lecture is going to be about the synthetic controls, so let's go for it. So synthetic controls were originally developed to estimate the effects of large aggregate events, and in particular, the effects of policy interventions that are deployed at the aggregate level, interventions that may affect entire cities or regions or countries. If you think about that, much of the available machinery that we have in economics and in statistics to estimate treatment effects is designed with the idea of estimating an average treatment effect over some population, and from that population we have extracted a large sample of individuals. Some of them are treated, some of them are not treated, and we are going to compare them in some way. However, like many of the policy interventions that we care about, or many of the aggregate events that we care about, well, they are not like that. They do not happen at the individual level. They happen at the level of large jurisdictions, as I said before, like cities, regions or countries. And even if you are in an experimental setting where the experimenter has the freedom of, deploying the intervention at a micro level or at a macro level or at an aggregate level, the experimenter may not want to do it at the micro level because, there may be like a fairness considerations. For example, if you have two individuals in the same location and one is treated and the other is not treated, this could raise like issues of fairness. And also you may have like interference issues. You may have like two individuals in the same locations, one is treated and one is not treated, but they are interacting, and like this is creating a bias in the experimental estimate. So to avoid all these type of issues, you may want to implement your intervention, not at the micro level, but at the level of a city or a school district or a region. Synthetic controls have been applied to study a variety of problems empirically, like from immigration policy to the effect of corporate political connections. They have been adopted as the main tool for data analysis, across different sites of issues in prominent policy debates on, like immigration and minimum wages. And they are also applied to outside economics, in the social sciences, in biomedical disciplines, especially in epidemiology, in computer science, and so on. They have also been widely adopted by multilateral organizations, think tanks like business analytics units, etc. And for example, a synthetic control method plays like a big role in the official evaluation of a massive educational program funded by the Gates Foundation. And while I think it is fair to say that the econometrics methods are not a daily staple of the popular press, and I guess this is a huge understatement, synthetic controls methods and their application have at times managed to capture the attention of journalists and of the general public. So what is my goal for the talk today? So I want to provide an introduction to synthetic control methods, describe some of the advantages of this methodology, which in my mind is explain the popularity that I have described before. And I also want to talk about some recent developments, like in synthetic control estimation, and I will finish with some remarks about potential avenues for future research. So that's what I'm going to that's going to be the next 50 minutes. Okay. Something that I should say is that many people have contributed to our understandings of synthetic control methods and related methods, like I don't know, in economics, like Hideo Inference, Victor Chernuchowskot, Bruno Furman, Jesse Rostein, and co-authors, and in statistics, Avi Feller, David Blay, and co-authors. In computer science, you have Deva Brasano, his group in MIT, and the literature is very large, and I won't have time to cover all this, and I will basically going to concentrate in the original formulation of synthetic controls, although there are many important extensions, many important related methods that are out there in the literature, and of course there are many empirical applications that I will not be able to cover. Okay, so let's start about what synthetic controls are about. Synthetic controls are based on the observation that when you have, as I described before, a few aggregate units are the units of the analysis, then a combination of comparison units, what we are going to call a synthetic control, is often going to do a better job reproducing the characteristics of the treated unit than any single comparison unit alone. Okay, and motivated by this consideration, a synthetic control is going to be selected as the weighted average of all potential comparison units, but we are going to choose this average in a way that best resembles the characteristics of the treated unit. And when I say characteristic of the treated units, I'm thinking about, like predictors of the outcome of interest. You will see in a moment. Okay, so like to formalize these concepts, let's introduce some notation. Suppose that we have like a j plus 1 units, t periods without loss of generality. Unit 1 is exposed to the intervention of interest after period t0, and you have like the remaining j units that are untreated, and this is what we are going to say they are an untreated reservoir of potential controls. We will call them the donor pool. This is the set from which we are going to choose our potential comparison. Okay, or the comparison for the treated unit. And this is going to be a framework of potential outcomes, like we will have YIIT and YNIT. These are going to be the outcomes that will be observed for unit I at time t with and without the intervention, respectively. And what we aim to estimate the effect of the intervention on the treated unit in a post-intervention period, and this is going to be, of course, as always, the comparison between the two potential outcomes. The first one is easy. With that one we observe. We don't have to estimate anything there. But the second one is complicated, and all our effort is going to be concentrated in, in estimating this second object. So as I said before, a synthetic control is going to be a weighted average. So each potential synthetic control can be represented by a vector of weights. Okay, one weight for each unit in the donor pool. And all the weights are going to be like a non-negative, and they are going to sum to 1. And we do that to avoid extrapolation, although this restriction could be relaxed. And in fact, they have been relaxed in the literature. Okay, so how are we going to choose among all these like potential synthetic controls? Well, we are going to, specify a vector of characteristics for the treated units, and again, these are predictors of the outcome variable of interest. This is a k times 1 vector, and we are going to have a matrix with the same values for the same characteristics for the units in the donor pool. And our vector of synthetic control weights is going to be chosen to minimize the discrepancy between x1, the characteristics of the treated unit, and x0w, the characteristics of the synthetic control, like subject to the weight constraints that we have that we described before. Okay, and now once we have this W star, like the estimation of the treatment effect in the synthetic control framework is easy. Like your estimate is going to be just the outcome for the treated unit and minus the outcome for the synthetic control. And this comparison, you can do it period by period, after the intervention. Okay. In the previous slide, I used a norm, but I did not define it. And in fact, there is a lot of flexibility in what you can use there. But most people use like some type of weighted Euclidean norm, in which these weights here, these constants, are going to reflect the predicted power of each of the predictors. And these constants, V1 to Vk, that are these weights for each of the predictors, can be chosen by the analyst directly, or can be chosen in a data-driven way. So let's look at the first application of a synthetic control estimation. This is an application to the effects of the German reunification on GDP per capita in West Germany. So what we see in the figure on the left-hand side is the series of GDP per capita for West Germany before and after the reunification in 1990. And we also see the same series for a sample of OECD countries. And something that you notice here, like almost immediately, is that here we don't have the usual conditions that we want to have to apply something like difference in differences. We don't have parallel trends. In fact, the trends before the German reunification for West Germany and for other countries in the OECD are quite different. However, what the figure on the right-hand side shows is that there is a combination of countries in the OECD that very well reproduces the trajectory of GDP per capita for West Germany before the reunification. And as we will see later, it is also going to reproduce other characteristics, other predictor of the outcomes for West Germany. Okay, so like you can see, the match is very, very close. And I guess that some of you may be thinking like, okay, I know what these guys did. They put all the values to get the fit that good. You probably put all the values of the outcome variable in the pre-intervention period. You put all of them into X1, okay, in order to have this fit. And in fact, we didn't do that. We did something very different. We just took, the average over 10 years before the intervention, and that's what we put in the X1, okay, and then like other predictors, okay, but you can see when you fit this average, you fit the whole trajectory very well. And why is that? Well, if you look at the raw data, you can see that there are some countries in this sample that they are co-moving very nicely. They are co-moving very strongly, and this co-movement between countries is exactly what the synthetic control is trying to exploit, and that's why we can fit this series, quite well. Okay, so what is X1 in this case? So we have here X1. These are like predictors of economic growth that are typically used in the literature, and these are the values that we observe for West Germany, and these are the values here that we observe for the OECD sample. And you can see that West Germany is not very close to the average of the OECD sample, even when we are already using a sample of industrialized countries. Okay, but however, what we can see also in the second column is that there is a combination, there is a convex combination, a weighted average of all these countries in the OECD that very, very closely reproduces the characteristics of West Germany. Okay, and this is going to be our synthetic control. This is going to be the comparison that we are going to use. And if you are thinking about, so what is this synthetic control for this problem? So here we have like perhaps not very surprisingly, Austria carries a large weight. Also like Japan, the Netherlands, Switzerland, and the United States, they carry positive weights, and the rest of the countries have 0 weights. Okay, so like as you can see, this synthetic control is sparse. This is something that is typical of synthetic controls, and we will see why later, and which makes the interpretation of synthetic controls particularly easy. Okay, so what are the properties of these estimators? One could ask. To establish the properties of the estimator, we are going to adopt some type of, benchmark model for the, like a benchmark model, generative, some model that is going to generate the outcomes, okay, of interest. And by the way, this is only the potential outcome without the treatment. As I said before, the outcome with treatment I observe. So, I don't have to, I don't have to assume anything about it. My only assumptions are going to be about what happens without the treatment. And in this are simple linear factor model in which the outcome is going to depend on characteristics of the units that we observe and characteristics of the units that we don't observe. And they come with coefficients that vary with time arbitrarily. And also we have like an individual transitory shock epsilon that we are going to model as random noise. And suppose that we can choose W star such that we can reproduce the characteristics of the treated unit, and also we can reproduce the trajectory of the outcome for the treated unit before the intervention. Suppose in fact that we can do that for any value of epsilon. And in practice, this this restriction may only hold approximately. Then we can establish a bound on on the bias of the synthetic control estimator. And here is for completeness, I have here like all the elements of the bound, and like is this a complicated object, but I only want to focus on something that we have here inside this max. We have these ratios, and these ratios are these two objects, and these two objects are related to the scale of the transitory shocks epsilon, and in the denominator we have like functions of the T0, that is the number of pre-intervention periods. And remember that to get this bound, we need this to happen. Okay, fine. So what are the implications of all this? What are the implications of this bound to the bias? Well, the first thing that we have to remember again is that this bound is predicated on close fit, and it is controlled by the ratio between the scale of the transitory shocks and the number of pre-intervention periods. That means that the credibility of synthetic control is going to depend on the extent to which you can approximate the trajectory of the outcome variable for the treated unit for an extended pre-intervention period. So T0 has to be large. The variance of epsilon cannot be very large. Otherwise, you're not going to be able to fit this trajectory. There are no ex-ante guarantees on the fit. Like sometimes you are able to fit, sometimes the unit may be very extreme and you are not able to fit. And if the fit is poor, like we will recommend against using the synthetic controls, or at least against using the, this vanilla version of the synthetic controls. There are some things that you can do about it, like bias correction, that I won't have time to discuss today. Okay. We have to be aware that, settings perhaps with a small number of pre-intervention periods, large number of units in the norm pool, and large noise, like a large variance of epsilon, they create substantial risk of overfitting, in the sense that you are not fitting the outcomes because the characteristics of the units, the Ci and the mu I, are similar. You are fitting the outcomes because like you have enough variation in the epsilons, and from this variation in the epsilons, you can fit. You give me enough noise, and I can fit anything. Okay, so to reduce so what we are going to do in this setting, I think like one good piece of advice is to restrict the donor pool to units that are similar to the treated unit, as we did for the German reunification example. We look only at countries in the OECD. For example, you wouldn't want to fit a country that like a middle income country with a country that is like a very rich, and a country that is very poor, because that will create interpolation biases. But also like you may be aware of the risk of overfitting, and having like a lot of units in the donor pool. You may be risking like doing some overfitting and therefore having like some bias. So what about inference? Inference in this setting, like inference for the synthetic control method is complicated by the fact that we are estimating the treatment effect typically for one unit. So standard asymptotic tools do not apply in this context. And to address this problem, we are going to base our inference on permutation methods. So basically what we are going to do is we are going to create a permutation distribution by iteratively reassigning the treatment to all the units in the donor pool and estimating these placebo effects in each iteration. And then the effect of the treatment on the unit that is affected by the intervention, we're going to say that this effect is significant when the magnitude of the estimated effect is extreme, relative to the permutation distribution. This is the way in which we are going to do inference. There are other ways to do inference in the synthetic control methods, but again, I am looking today only at the original formulation. For example, Matthias and Rocio, in fact, have done some very nice work on doing other modes of inference in synthetic controls. Okay, so let me try to explain with an example how this permutation inference work in practice. So here we have our test statistic, computed for West Germany and computed for all the countries in the North Pool. And we can see here is that West Germany is very extreme, in this distribution. And by the way, and if you look at the test statistic, it's not just the treatment effect that we estimated. It's what we have here is the post period or post-intervention root mean square error divided by the pre-intervention root mean square error. Why is this? Well, when you look at all these units in the donor pool, some of them can be fit. You can fit them very well in the pre-intervention period, and some of them you can fit them not so well in the pre-intervention period. So that's why we are going to take this root mean square error, that is the difference between the the trajectory of the outcome for for the treated unit in the post-intervention period, and the trajectory of the synthetic control for that. The synthetic control that correspond to the treated units, we are going to divide it by the same difference in the pre-intervention period. Okay, that will be. I will explain this this idea, a little bit more later. Okay, some remarks about this type of permutation inference. The first one is that clearly, looking at the permutation distribution is much more informative than mechanically looking at p-values, because you can see, how far away, the test statistic is relative to the, a permutation distribution. P-values only give you the ranking. The second remark is that depending on the number of units that you have in the donor pool, conventional significant levels may be unrealistic or maybe impossible, right? If you have like 19 units in the donor pool plus one treated unit, then you can hope for, having a like a p-value equal to 0.05. Otherwise, if you have less, you have fewer, you won't be able to attain, like 0.05 p-value, which, is something that some people really insist in doing. And something else that, it is going to be, I hope, clear in a second example is that the one-sided inference is often more relevant and is often, like more powerful. We will see that in this second example. This is an example about applying synthetic controls to study the effects of a tobacco control program that was approved in California in 1988. And what we can see here is like at the series of per capita cigarette sales in California, and before and after the passage of this regulation, the passage of this law that was is referred to as Proposition 99, and we have also the same series for the rest of the US. And again, this is a setting in which you wouldn't want to do like difference in difference, right? The trajectory of the outcome variable is completely different for California and the rest of the US. If I do difference in difference between this point and this point in time, I'm going to get something, but like there is no intervention there. Okay. However, like as for the German reunification example, there is a combination. There is a weighted average of other states in the United States that is able to reproduce the trajectory of tobacco consumption in California before the passage of Proposition 99, and also other, I won't talk about this, but also the predictors of tobacco consumption. And as before, we want to say, that this, this what we observe there is the effect of the intervention. Okay, so what we are going to do in order to understand the inferential procedure a little bit better is like we are going to plot all these differences. We are going to plot all these differences in time between, California and the synthetic version in California. And if you do that, you obtain this graph, right? Like we have fitted California very well, in the pre-intervention period. There is a gap in the post-intervention period. Okay, so what is the permutation, like inference based on? It is based on the idea that now we are going to go to our data and artificially we are going to reassign, the treatment to the other units in the donor pool and see what happens. Okay, so here we are. These are all the synthetic controls for all the units in the donor pool. And something that you see here very clearly is that, and not very surprisingly, is that there are some units that they are so extreme that are the extreme of the distribution of the outcome that you cannot fit very well. Okay, like tobacco consumption in Kentucky is too high, and tobacco consumption in Utah is too low to be so that we can reproduce it using a weighted average of other, tobacco consumption in other regions. So while although the estimate for California is really extreme, in this permutation distribution, the comparison is not even fair, right? Because it's like we are, including here like units that we cannot fit very well, before before the intervention. Okay, if we take those away, let's do this. Now we have like only units that we can fit quite well, like units at the mean square prediction error, the difference between the outcome variable for California and for the synthetic control, like it's not more than twice, the units with mean square error, that is not twice the mean square error for California. So the mean square error here is the difference between the outcome variable for California and the outcome variable for the treated unit and the outcome variable for the synthetic control. So we are only keeping those that we fit almost as well as California. Again, you can see that this, California is extreme in this distribution, and this two-sided, one-sided inference is useful in the sense that, if there is like a negative fit for California, California may be in a, in the synthetic control for, a placebo intervention, creating positive feds and adding to our statistical power. If you don't like this business of taking away units that you cannot fit very well before the intervention, you can do as before, like looking at some relation between the post-intervention fit and the pre-intervention fit, and you can see for this example, California is like a very, very extreme in this distribution. Okay. So let me talk about a couple of remarks about this permutation method. The first one is that it is the availability of a well-defined procedure to select the comparison unit what makes this the calculation of all these placebo interventions feasible. If we are going to choose a comparison based on some subjective measure of affinity between the units, it will be very difficult to reproduce that when you have to do it for like in many placebo interventions. The second point that is important to notice is that the permutation method that we describe now, it does not attempt to approximate the sampling distribution of the test statistics. And in fact, like sampling inference is going to be quite complicated in a synthetic control setting. Many times because we have the absence of a like well-defined sampling mechanisms, and often because the sample is the same as the population. So it is very difficult to think about what sampling inference means in this setting, at least like again in this original formulation of the synthetic control model. Okay. Many of you probably realize that this type of inference is going to reduce to classical randomization inference if the intervention is actively randomized. But again, remember that we are talking about a setting in which you have like a aggregate units like regions or countries, and like a randomization in this setting is quite improbable. It's something that it doesn't happen in general. But more generally, we can think about this mode of inference as evaluating significance relative to a benchmark distribution for the assignment mechanism, one that we can implement directly in the data. And in what I have shown before, this benchmark distribution is uniform, but it doesn't need to be uniform. Like you can use you can use departures from uniformity, and Sergio Firpo and Possebon have like a paper about this in the journal of causal inference. Many times people ask me like, why don't you use something like a propensity score method? And that is kind of a complicated, because it is in these settings with aggregate units, it is often difficult to articulate the nature of the assignment mechanism or even the specific nature of the placebo intervention, right? I was discussing yesterday in another meeting about think about what would be a placebo intervention in the German reunification example, like France is going to get reunified with whom exactly, right? This inference is relative to like a benchmark distribution, but it's not based on active randomization in the field. Okay, so now I will try to think about and discuss what are the advantages of these synthetic control methods, why we may want to use them. And in order to illustrate the advantages, I'm going to compare synthetic controls to regression analysis. That is a very familiar estimation framework. And in fact, years ago when we started talking about synthetic controls and we will go places, to present this work, people will ask, why don't you just run a regression and instead of doing this thing of like a combination of weights of sum to one, can you do this using regression? In fact, you can do this using regression, right? And we have it here. Like you can take all the outcomes of the units in the donor pool in the post-intervention periods. These units are not treated in the post-intervention period, and we are going to regress them on the characteristics of these units. And I put a bar because I have augmented these metrics of characteristics with a row of 1, because I want I'm going to have like an intercept in my regression as usual. But once I have that, I know how to estimate regression coefficients with the usual formula. Okay, and each column of this beta hat is going to be like the the regression coefficients for one of the post-intervention periods. Okay, and now how am I going to use this to calculate a regression-based estimate of the counterfactual of interest? That is, what would have happened with the treated unit in the post-treatment period without the intervention. So that's going to be, like a, my usual like a regression estimate that is going to be beta hat multiplied by, the characteristics of the treated unit. Okay, so now something that is easy to see, given the formulas that we have so far, is that this regression-based counterfactual, in fact, looks very, very much like a synthetic control. It is also like a combination of the outcomes of the untreated units in the post-intervention period. Okay, and you could calculate the weights. These weights, we usually don't do it when we run a regression this way, but you could calculate these weights explicitly. And given the formula that we have for these weights, you can also prove that these weights sum to 1. Exactly like for the synthetic control. So what is the difference between, like doing this with regression and doing this with synthetic controls? Well, the difference is that these weights here, they may be outside of the 0-1 interval. And we know that we should allow that because, regression extrapolates. It's going to extrapolate to fit the values of the characteristics of the treated unit. Okay, it cannot be only based on interpolation. Okay, and also as we will see in a moment, these weights are not going to be sparse. Okay, so a nice exercise, something that we can do is to calculate these weights for one of the like examples that we consider so far, and these are the weights for the example of the German unification. These are the regression weights. Remember, the synthetic control weights were sparse. They were all of them, they were positive, and non-negative, and most of them were 0. Here you have like a non-sparse weights, and you have like some of them that are negative. And this is like a little bit more difficult to interpret, or much more difficult to interpret, the nature of this estimated counterfactual, because now perhaps, the contribution of Austria perhaps is moderated by, the negative weight of Italy or Greece. Okay, and it's very difficult to figure out what's going on here, and that's the cost that you pay for not having sparsity. So what are these advantages of synthetic controls? The first one is like a no extrapolation, like a synthetic controls preclude extrapolation by using weights that are in this interval in between 0 and 1. The second one is transparency of the fit, like linear regression is going to extrapolate, so you can show that it's going to fit the characteristics of the treated unit perfectly, even if the untreated units are completely dissimilar in their characteristics, and they are very far away from the treated unit. In contrast, synthetic controls are going to make transparent the actual discrepancy between the treated units and the convex hull of the units in the donor pool. Also, unlike in regression analysis, we don't need data on post-treatment outcomes in the design phase of the study when we are trying to calculate this vector W star. To calculate W star, we don't need any data on outcomes after the intervention. Therefore, all design decisions, like we can make all of them without knowing how they are going to affect the conclusions of our study. Not only that, like these synthetic control weights can be calculated and pre-registered before even post-intervention outcomes are realized or before the actual intervention takes place. Okay, and this provides a safeguard against specification searches and p-hacking, something that is worrying many people now. Okay, the last two points are related. The first one is transparency of the counterfactual. Synthetic controls make explicit the contribution of each comparison unit to the counterfactual of interest. It's a weighted average is easy to interpret, especially when it is sparse, because the synthetic control coefficients are proper weights and they are sparse. They allow you to have a precise interpretation of the nature of the estimate of the counterfactual of interest and of potential biases. For example, if you think, no, I think that Austria in fact was affected by the German unification, you can immediately see how this is going to bias your estimates. Okay, so we have mentioned a couple of times that synthetic controls are sparse, and here we have the explanation, like a geometric interpretation of this sparsity. you can think about a synthetic control. What if this synthetic control is a projection of x1, on the convex hull of the characteristics of the units in the North Pole, and like that we obtain the synthetic control. So if x1 does not belong to a convex hull, and this is typically the case because of the course of dimensionality, then the synthetic control is going to be unique and sparse. If x1 belongs to the convex hull, the synthetic control may not be unique, and you will have candidates. Typically, you will have candidates for a synthetic control that may not be sparse. Okay, typically you will have an infinite number of solutions, although we know that there are sparse solutions among them. Okay, and the question is how we can decide among all these many solutions, and can we get a one that is optimal in some way, and is this optimal solution going to be as sparse as before? And this is related to one of the new techniques in the synthetic control literature. It's called penalized synthetic control estimators, and penalized synthetic control estimators are going to be very much like the usual synthetic control estimators, but they are going to add this term to the objective function. And this term is penalizing the discrepancy between the characteristics of the treated unit and the characteristics of each of the unit that contributes to the synthetic controls. So when this lambda is positive, it's going to control the trade-off between fitting well the treated and minimizing pairwise matching discrepancies between the treated units and the units in the synthetic controls. If you take this estimator, you calculate this estimator and make lambda, going to 0, and the resulting estimator, in fact, can be calculated, with an approximation. They are mathematical techniques to do that. This is what we call the synthetic control, and this is going to minimize the pairwise matching discrepancies among all solutions for the penalized estimator. And not very surprisingly, when if you make lambda go to infinity, then only the pairwise matching discrepancies matter, and then you will get the nearest neighborhood matching estimator. That will be the solution. And so what are the advantages of the penalized synthetic control estimator? For lambda bigger than 0, the solution is going to be unique, and you will see that it's going to be sparse, and we will see in an example that is going to be sparse, although this is like a general mathematical result that I'm not going to discuss. And the presence of the penalization term is also going to reduce interpolation biases that occurs when you average units that are very far away from each other, and you can show that has the same computational complexity as the penalized estimator. So it's not more complicated to estimate. To understand how the penalized synthetic controls works in practice, instead of giving you the formal result, I would like to think about a very, very simple example. This is as simple as it can get. I mean, we have a one treated unit, 3 untreated unit. Unit 1 is a treated unit. We have 3 untreated unit, and X is one dimensional. We only have one dimension. Okay, and so you can see here that the unpenalized synthetic control estimator has 2 sparse solutions. The first one is the one that you obtain when you use x2 and x3 to interpolate x1, and in the second one you obtain when you use x2 and x4 to interpolate x1. Okay, but you immediately see that the first solution dominates the second solution in terms of the matching discrepancy. Okay, and it also is going to dominate an infinite number of non-sparse solutions that you obtain from convex combinations of the sparse solutions. Okay, but if you look at the original synthetic control estimators, all this infinite number of solutions look the same. I mean, in terms of the objective function, we need a way to discriminate among them. Okay, however, when you look at the penalized synthetic control estimator, as long as lambda is bigger than 0, the penalized synthetic control estimator is going to have a unique solution, and it's going to be sparse. In fact, you can see that it never uses the bad match x4. Okay, it never uses the bad match. As lambda goes to 0, it converges to W1 start. As lambda goes to infinity, it converges to giving all the way to x2. That is the nearest neighbor estimator. That's the way this works in practice. Okay, so this was like a little bit of a short summary of one new development, like in the literature of synthetic controls, and I want to talk about a second one, and this second one is like using synthetic controls for experimental designs, and what is this about? Let me try to explain this with an example. Suppose that you are in a ride-sharing company, like something like Uber, and you are thinking about, a different compensation plan for workers, for drivers. Okay, and you think, okay, so like we have the usual compensation scheme and a new one, perhaps with higher incentives to drivers. And which one we are going to use? You are in the business analytic unit of this company. So something that you could do is say is like, okay, so I will go to a city and I will assign some workers and like to the new compensation plans and some workers to the old compensation plan and see what happens. But as we described in the first slide, this is going to be problematic because you have like workers in the same cities, like getting different amount of money for the same work, and that will be considered unfair, and it is unfair. Also, like the problem is that like if Rocio is like in the high compensation plan and I'm in the low compensation plan, probably Rocio is going to work longer hours because has higher incentives, as she may be still in business from me. So there will be all these type of interference issues that we make care about when doing an experiment. So what we may decide is like, no, what we have to do is to deploy or treatment at the level of the entire market. Okay, and perhaps we don't want to do it like treatment for 50% of the markets in the United States and no treatment for 50% of the markets in the United States. That could be super costly, perhaps, and also like it will be a little bit of a nightmare if if you decide to roll out or if you decide not to implement the better compensation plan at the end of the experiment, right? So you may decide, okay, so I'm going to apply a pilot program in one market or in one city or in a few markets and cities, and I'm going to try to see what happens there. Okay, so in this case, you don't want to randomize. Okay, and you don't want to randomize because if you are going to apply this program to one city, like the city that you can get may be one that is not maybe not representative of the entire market of the United States, or maybe one that you cannot reproduce very well, that is especially idiosyncratic. And randomization will give you like unbiasedness ex ante, but I suppose you may be like in big trouble. So you want to your experiment, you want to do your intervention, but in a non-randomized way. Okay, and the question that you are going to ask yourself is, which market or markets should I treat, and which market or markets should I use as a comparison or as a control? Okay. So what we have proposed in this setting is using synthetic controls. First, you find a set of weights that make a synthetic unit that reproduces the characteristics of the population of interest. For example, like all the cities where I have where my company is operating in the United States. And then you're going to create a synthetic control for the synthetic treated unit. Okay. And in contrast with the observational case, here we are going to have two units, one synthetic treated unit and one synthetic control units. Okay, and these two objectives you can operationalize, put them in a nice objective function that you need to maximize, and this is what is going to give you optimal designs in synthetic control settings when you are doing experimentation, not randomized experimentation with aggregate units. And we have some work on this, and also Nick Dowchenko and others have been working these kind of techniques. And I have to say something about this, is that this is kind of new to academia, but it is not new to industry. Many companies are applying this type of synthetic control designs for experimentation, exactly because of the type of issues that we were talking about in the previous slide and this slide. And what we are trying to do here in this work is to try to formalize, many of the things that are already being applied, like in industry. In academia, sometimes we have like less capacity of randomizing across big aggregate units, okay? But sometimes happens, like sometimes we do that in like with villages and so on. Okay, so I have some time, but it seems that I went fast enough, so I'm ready to give closing remarks. And what I've been trying to say is that synthetic controls, is they have gained popularity, but the reason that why they have gained popularity, in my view, is because they have many practical advantages of design for the estimation of treatment effects, especially in settings where you have like a few aggregate units. Some of them are, exposed to intervention of interest, and some of them are not. Okay, I didn't have the time to talk carefully about what are the requirements that we need for synthetic controls to work in practice. We saw some of that when we talk about the bias-bound formula, but as I said before, as for any other statistical procedure, and especially those that want to estimate causal effect, the credibility of the result that you're going to obtain depends very much on how diligent you are, applying these methods, and the type of data that you have, and contextual characteristics of your problem that have to be met. And I have a paper, a recent paper in the Journal of Economic Literature that covers cover all these aspects in quite a lot of detail. So what are some open areas of research for synthetic controls? Well, this is quite a new method, so there is a lot that has not been done, and some people have been working on sampling-based inference, although, in my opinion, there still is quite a big open field in terms of potential improvement. Not much has been done in terms of external validity, sensitivity to model restrictions. There is some work with estimation with multiple interventions, but also very interesting set of issues. And also much more work needs to be done on data-driven selectors of VH. You remember these were the weights that we put to the variables, to the predictors that we're using for estimator, and other things like mediation analysis. There is very little work done for synthetic controls, and it's something that my guess is that is going to happen in the next few years. And also another area that is a favorite of mine, as you could see before, that is of a high interest, is the use of synthetic controls as experimental designs. And there are many contexts, especially in industry, but also in academia, where we need to carry out experiments at an aggregate level, and we lack a lot of tools for doing that. Most of the tools we have today is for the case in which we have many micro units that are treated and many micro units that are not treated, and this is not exactly the case. And this is interesting because it make also this a case in which the availability of methods may restrict what you do in practice. I mean, sometimes people tend to do what we know how to do, and this is a a new set of potential experimental designs that could be used quite a lot in practice. Also on computation, this is important. We need many more results on robust and efficient computation of synthetic controls, and the good news about this methodology is that on the empirical side, many of the event samples interventions that we care about do take place at an aggregate level and affect the entire aggregate unit. So there is a lot of many possibilities, many potential empirical settings where we can apply these methods. So let me finish looking a little bit at some resources that I have used in this presentation and some extra resources that that you can use for synthetic controls. Most of my material in this presentation comes from my own work, and this is and you have the reference here, and in particular, like it comes very directly from a recent paper in the Journal of Economic Literature on feasibility, data requirements, and methodological aspect of synthetic controls. There is also like some information here about like a code for calculating synthetic control estimators, calculating the unpenalized synthetic control estimator, also calculated the penalized synthetic control estimators. And as I said before, like many people have contributed to the literature on synthetic controls, and I wanted to provide some references here, so like you can access this material. And I hope that these slides are going to be available after the presentation. Okay, and that's all I have. Thank you very much.